I guess I'll get started, guys. Let me begin with a word of prayer once I get up here. Dear Father, we thank you for this day, and I thank you for these students, and just ask you to bless our work today. Help us to understand a little bit more about your creation together, Lord. In the name I pray, Lord Jesus. Amen. So, yes, this is. I'm about to give you an intensive and complex analysis. I can't offer any credit for it. Although, if you do spend about another 200 hours on homework, then you should be prepared to take the ICE exam to pass out of the course. But don't do that. Instead, take it with Dr. Majerick in the fall. But anyway, let's just get into it. So my goal in this talk is to teach you complex analysis. And so we have to start at the beginning, which is complex numbers. Of course, complex numbers have a real and an imaginary part, and you multiply them like this. The interesting new thing here basically is that I squared is -1, right? This notation I, introduced by, I think, Euler in 1700s. No, 1800s, but 1733 or something. I don't know. Maybe it was 17, who cares? Anyway, so anyway, this is how we multiply complex numbers, and you can take the complex conjugate of a complex number. And what's interesting then, of course, is that the length of a complex number you can get from taking the product of the number and its conjugate. So this is very special. It means we have a formula for the length of a complex number as the square root of the product of the conjugate and the number. And a homework exercise I often put on test 1, and it's supposed to be a gift, but it's usually not freely taken by the students, is to prove that the product of the conjugates is the conjugate of the product. This is easy to prove, and once you know that, a straightforward consequence of that is that if you multiply two complex numbers, the product of their lengths is the length of their product, which is very unusual if you study more general algebras. So anyway, there's that. And then the other really interesting thing about complex multiplication is it naturally encodes two-dimensional rotations. So for example, if you put a complex number in polar form, so we introduced this imaginary exponential, which is simply cosine theta plus I sine theta. Hopefully you've seen that somewhere in one of your courses at this point. And if you do that, then we can write the complex number in polar form like this. And if we have two such numbers, when we multiply them, we see that the magnitude of their product is the product of their magnitudes. In other words, what I was just talking about, the product of the length of the product is the product of the lengths. And also, interestingly, the angle is you just add the angles, right? So what this means is that if we multiply a complex number by e to the I theta, what it ends up doing is just rotating the number by theta in the plane. So if we want to encode rotations in the plane, complex notation, super nice. I've actually tried to get my differential equations class to use this to solve a homework problem this semester. I'm not sure it works or not, but I'll find out soon from the grader. So once you have complex numbers, you can define functions, all kinds of complex functions to define. Of course, one of the principal ones is the argument. The argument's just basically a choice of standard angle. By default, we go from minus pi to pi, and we don't include the minus pi. We do include the pi, typically. And then what that means then is that that's basically just the standard angles. That's a choice of standard angle, all right? And much of the suffering in complex analysis, much of the suffering in Math 331 comes from the ambiguities that are brought in by this choice of angle, because it is nefarious and it will get you when you least expect it. It's fussy. Now, we can also define complex exponential function, which is, you notice it's got the regular exponential function, but also this imaginary exponential thing. So the complex exponential simultaneously folds in the real exponential function and also sine and cosine all at once. You can also define the logarithm of a complex number. So you suppose you want to take the log of a negative number. In Math 331, we learn how. This is how. You just use this formula right here. The angle for a negative number is excuse me, pi. So what that means then, if I was to say take the natural log of -5, excuse me, not the natural log, but the principal log of -5, what that would be is natural log of 5 plus I pi, right? So we don't talk about that in pre-calculus because, if you start doing imaginary values for your logarithms, they're all going to revolt, right? They're going to go en masse to Professor Young and say, this guy's crazy. stop him. And then Professor Young will be like, I already know, deal with it. But no, I just won't do that. Probably. Maybe on the cusp of retirement, I might do complex values in like a pre-calculus class just for kicks. So you can also define the complex power function. So this is like a kind of sneaky way to build z to the power c. You put the c here, so it's kind of like basically building in the power property for the logarithm, but this actually serves to define like z to the I power or something. All right, this is how we define something like that. The sine and the cosine at the start of the course, I'll give these transitional definitions. So we can build sine, cosine, cosh, and sinh all from the complex exponential like this. All right. Now later, from a more mature viewpoint, I would say define sine, cosine, cosh, and sinh by power series, which we'll get to, but one thing at a time. Now, classically speaking, one of the great difficulties of complex analysis is that you can make these choices. Basically, anytime in these formulas I've used a capital arg or a capital log, I'm making a particular ad hoc choice of standard angle to build the formula. All right, and you could make other choices. Those other choices are reflected in these constructions down here. These are multiply valued maps. Perhaps the most interesting one is the nth roots of z. So you take the principal nth root, which is this business here, and then if you multiply it by any of these guys, any of these will give you another number. Basically, if you take this times any one of these, if you raise that to the nth power, you get back z. And these, I should maybe draw a picture of those. I didn't have it. Ran out of time. I would like to include some more pictures in this talk, but oh well. Guess you can't let perfect be the enemy of good or whatever. But so it's something like this. So this might be like omega. How many did I do here? 1, 2. I guess I got one up here too, huh? Maybe I don't know what am I working with here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe this is omega 10. This is like omega 10 squared. I'm not doing it exactly, so I'm going to back off that picture because at some point, those of you who know more are going to call into question the placement of my dots. So let me fix this. How about we do something a little bit more cut and dried, like 1, I, minus 1, and minus I. So here, I is the principal fourth root of unity. This is e to the 2 pi I over 4, which is e to the pi I over 2, which is cosine pi over 2 plus I times the sine of pi over 2. But you guys know what sine and cosine of pi over 2 is, right? So that's just 0 plus I times 1, also known as I. So what you're looking at here are the principal fourth roots of unity. These are the numbers whose fourth power gives you back the number 1, all right? And more generally, if you have an nth root of unity, you can take the principal nth root, constructed, well, I don't have it here. Oh, there it is. Like so, and this gives you n distinct principal nth roots of unity that symmetrically arrange themselves around the unit circle. Fun question for you guys. What do you think the sum of all the principal nth roots of unity is? If you add them all up, what would you get?
Yes.
0, right, because they're like symmetrically distributed around the origin. So if you add them up, you get 0. I actually needed to use that in a paper I wrote with King a few years ago. Somehow, some argument we had used that. But anyway. All right, so this should be a little bit more familiar in some sense or another. We can look at a polynomial over the complex numbers. It's just like the polynomials you guys would look with real variables. It's just now the coefficients can be complex numbers. There's something called the fundamental theorem of algebra, which says that every non-constant polynomial over the complex numbers has a 0. And if you have that, it follows that you can factor it completely into a product of linear factors, of course possibly repeated. Here's an example where I factor z to the fourth plus 16i using that fourth root thing I just showed you. So like, all right, so to find the zeros of this, I'm looking for where z to the fourth plus 16i equals to 0, right? So that's the same as z to the fourth equals to minus 16i. But minus 16i, I can rewrite in polar form like so, right? It's got like angle minus pi over 2. You can kind of see that in the picture I drew over here. And anyway, so the principal fourth root of minus 16i is actually 2 times the exponential of minus I pi over 8. And since the fourth root of unity is I, like I just told you guys, it follows that these are the principal fourth roots of minus 16i, namely these 4 numbers. And then if you work it out in polar form, that gives me minus pi over 8, 3 pi over 8, 7 pi over 8, and 11 pi over 8 as my angles here. And so there you go. I've factored z to the fourth plus 16i using this technology. Here's 5 numbers who raise to the 5th power of minus 1 if you wanted to find them. And again, it's using that same 5th roots construction. Now, these things were known to Euler, right? So like, just to take a step back into the history for a second, the solution to the quadratic problem has been known since like Babylonian times. Like for a long, long time, we've known solutions to the quadratic formula. But the solution to the cubic and the quartic formula came much, much later, right? Do you guys know? When?
16?
Yeah, I think like the 1500s or the 1600s, somewhere in there. Like, what's his name? Yeah, Cardano, Tartaglia, these guys. So it was fairly quickly after they found the solution to the cubic problem that they found the solution to the quartic problem, right? My wife actually learned these in high school, like this actual solutions. They're quite hideous. But you might see them in like Math 422 here, all right? And so, it seemed like that mathematicians were going to then find solutions to the 5th order problem and 6th order problem. Like, in other words, to write the polynomial equation in terms of a sum of products of the radicals of the coefficients and so forth, right? The quadratic-like formula for higher order problems. But after monumental work by like Lagrange, Euler, and others, it became clear that there was no 5th order problem, right? So in the early 1900s, about 1820, there was a fellow who wrote this down. He said, go to the roots of these calculations, group the operations, classify them according to their complexities rather than their appearances. This, I believe, is the mission of future mathematicians. This is the road on which I am embarking in this work. Do you guys know who this is a quote from? I mean, he was alive in 1820, so he's dead now, but he was actually dead not too long after this quote. Galois, yeah. So Galois, basically, these same rotations I'm showing you in the plane, studying how you can take one solution and sort of rotate it into another, that idea of there being some kind of structure within the roots ultimately gave rise to what we now call Galois theory, or Galois theory, if you want to offend people. But of course, some of you are taking a class in that right now with like Dr. Sprano, so, which is pretty awesome. All right, so algebra aside, let's move on to calculus. I've only got about 30 minutes left, so I better get with it. So differential calculus over the complex numbers, it can start out at least, pretty much the same as what you guys have already seen in Calculus 1, right? You remember the difference quotient that you all love? You're math majors, you love it.
Yeah.
All right, this is, how dare you? How dare you? All right, so anyway, so the difference quotient that math majors are supposed to love, although I have bad-mouthed it as a professor once, like not professor, as a grad student, only to get a stern talking to by the numerical methods guy who was shadowing me, and all of his research was based on like feeding data into a actual difference quotient. Oops. But short of that guy, pretty much none of us use limits directly, right? Like we get past a certain point of theoretical interest, and then we start using the rules of calculus. And you'll notice that the rules of complex calculus are really just the same as the calculus you already know over the reals, right? You got a sum rule, you can pull constants out, this is the chain rule, power rule, derivative of sine is cosine, exponential differentiates to itself, derivative of the log is 1 over z. These are all familiar facts, right? So pretty much if something seems like it can work in complex calculus, by analogy to the reals, it probably does. Now, eventually that becomes not true, but not yet. Now, so of course we can define the complex derivative by difference quotient, but there is more to say here.
Sorry. Sorry, didn't and keep going.
Jackswar. All right. So there is more to say here, of course, because there are, in my view, there are like four sort of natural, well, maybe natural is too strong a word, but there are four perspectives on complex differentiation that I teach. The one is the difference quotient definition. The other one is common. Everybody talks about this. If f is equal to u plus iv, then it's complex differentiable. If this is a continuously differentiable function, which means just that the partial derivatives exist and are continuous, if that's true, and these relations between the partial derivatives exist, so like the x derivative of u is equal to the y derivative of v, and the x derivative of v is the minus y derivative of u. These are the so-called Cauchy-Riemann equations. If those equations hold, that gives you complex differentiability of the function. All right. So these are nice because, like something, for example, to prove that the exponential is complex differentiable, it would really be a drag to try to do it directly from the difference quotient. But it's pretty simple to check that the Cauchy-Riemann equations hold for the complex exponential. And that, of course, the component functions are like e to the x cosine y and e to the x sine y. So they're pretty nice. Now the other way to do it is the so-called Wirtinger calculus, which you define these partial derivatives, the complex partial derivatives, which are really just particular complex linear combinations of real partials. And if you do that, you can capture complex differentiability by the statement that the derivative with respect to the anti-holomorphic variable is 0. And in that context, the complex derivative just becomes the partial derivative with respect to z. This is perhaps the most efficient viewpoint, which essentially says the following. If your complex function can be written manifestly as just a function of z, it's complex differentiable. On the other hand, if your function involves like z bar, it's not complex differentiable. For example, if you look at the length squared function, f of z is z bar, all right? That's not complex differentiable at most places, because if you take the partial derivative of z bar with respect to z bar, you get z, because partial z bar is 1, and z and z bar behave as independent variables. So anyway, there's lots to say about that, and I can't say much more today. So my apologies for any kind of typos. There got to be typos in this thing. So if we look at holomorphic versus analytic functions, these are really different concepts. So the concept of holomorphic means, what that means is that your complex function is complex differentiable on some domain. Now a domain is an open connected set, all right? So to say it's holomorphic is to say it's complex differentiable on some open connected set. My example here is the logarithm. The logarithm has a trouble because the log z has that plus I arg piece in it. Like if you look at the formula I wrote for logarithm earlier, it involves the principal argument. The principal argument is a choice of angle. And see, there has to be a place where the angle jumps, which is why we can't get all the way around the origin. There has to be a place where you jump 2 pi for the angle, but that's discontinuous. It's still the case in complex analysis that if you have complex differentiable, it implies continuous. So it would be impossible to have a function that involves the argument, the principal argument, defined all the way around the origin, because it has to somehow get hung up on that angle jump, which gives you a point of discontinuity, which then stands at odds with the complex differentiability. So it's not a big defect, but there has to be a place. There has to be a place where the angle jumps, and that's a place where we can't maintain the complex differentiability. So for that reason, we look at these things called slit complex planes. So like this C minus is basically the complex plane with the real negative real axis thrown out. I'll draw a picture. So like C minus is just this thing. This is gone. The slit complex plane. So the logarithm, the principal logarithm, is holomorphic on the slit complex plane. So then, on the flip side, it's interesting. In fact, a lot of the complex analysis course is devoted to the study of functions which are analytic. What does it mean for the complex function to be analytic? Well, that means that you can represent, if it's analytic on this disk of radius r centered at z0, that means that there's a power series representation for the function. All right, and the function is also said to be entire if it's analytic on the whole of the complex plane. So for example, well, there's lots of examples. Sine, cosine, cosh, sinh, the exponential, polynomials, products thereof. These are all entire functions. For example, sine z, what's the power series that defines it? Well, guess what? You already know it. Or don't remember it from Calculus 2, depending on who you are. But maybe you do. So this is the, the usual Maclaurin series for sine. It's still true when you put in a complex z. And the same story for the exponential. This is the, you could take this as the definition for the complex exponential if you were so inclined. It would be a good definition. You can easily prove the properties of the exponential from like properties of multiplying series and things like that. So here's the deal. If we have f of z is analytic at z0 with a power series centered at z0, that means that f of z is given by power series. The radius of convergence in this case is an honest to goodness radius. It is the largest number r, such that f of z extends to be holomorphic on the disk as such. So basically, the rule in the complex context is like the domain of analyticity relative to a center point. It's as big as it possibly can be until you hit a singularity, at some point where you don't have the convergence of the of the power series. But it's especially satisfying because, of course, in Calculus 2 we talk about radius of convergence, but you might feel like, what's the radius? We're just looking at things on a number line. Well, now it's genuinely a radius, and everything kind of mystical in Calculus 2 is easily understood from an intuitive perspective when you study complex analysis. Oh, so I guess I better get to integral calculus because we're almost out of time. Well, that's not true. We still have time, but I still got a lot to say. So integral calculus, how you integrate a complex function, it's much akin to how you integrate a vector field in Calculus 3. Remember, we take a parameterization of the curve and we calculate with respect to that parameterization. We do something similar here. So maybe this is the easiest thing for you guys to understand if you know Calculus 3 well. If we're going to integrate the complex function f of z dz, where like f is u plus iv, all right, f is u plus iv, like up here, then basically all you do is write dz as dx plus I dy and just kind of multiply it out. If you think about it, you're going to have like u times dx, right? And you're going to have like iv times I dy. That gives you this minus v dy. You can factor the I out and you'd have like the u dy plus v dx. So you can formally expect this rule, all right? So if you look at my complex notes, I give two alternative competing definitions for what the complex integral should be. I mean, okay, to be fussy, you might want to define a theory of complex integration not just over like a path which is parameterized with just one thing. You might want to allow for a finite collection of paths that are strung together. This is sometimes called an arc. You do the integral over each like sub piece of the arc, and then you add them together to get the total integral. Kind of like how you learn to integrate piecewise defined functions in like Calc 1, right? Anyway, so if you look at it, a single complex integral, if you ask me what it is geometrically, I'd be like, go away. There's not a direct, I can't tell you like the area under a complex curve or something like that. No. At best, what I would tell you is it's calculating the work done by two different vector fields. It's calculating the work done by the vector field u comma minus v, and it's also calculating the work done by the vector field v comma u. And it's a complex linear combination of the work done by those two vector fields along the curve. I don't usually think of it that way, but you could. Here's an explicit calculation. So suppose you actually want to calculate the integral of dz over z over the unit circle. All right, so the way that's done is you parameterize the unit circle. And, well, there it is. That's the parameterization of the unit circle. See, the magnitude of the imaginary exponential. Remember, this is like cosine plus sine plus I sine. So the length of it is cosine squared plus sine squared square rooted, also known as 1. So this is an honest parameterization of the unit circle. And if we put z equals to that, then dz is I e to the it dt. See, the chain rule still works just like you'd expect. So then you just plug those two things into here, just like you do in Calculus 3, if you use the method of differentials there. And we, of course, have to put the integral from 0 to 2 pi, since that's the range of the parameter. And yeah, well, lo and behold, we get 2 pi I. So the integral of dz over z is 2 pi I. Now, that's kind of interesting, right? Because if you think about it, we're integrating something like a vector field around a circle, right? You might expect that should be 0. And indeed, it almost always is. So like this formula down here is my beloved Kronecker delta. What this says is that the integral of the power function, z minus z naught to the power n, it's 2 pi I and times 1 in the case n equals to minus 1. This, for example, is z naught equals to 0 and n equals to minus 1, the minus 1 power. What this says is that the integral of a power function, right, around where it's centered, it's 0 in every other possible power. Even when you've got division by a high power, all right? Like the only kind of divergence which ends up giving you a non-trivial integral around the circle is actually just the reciprocal divergence. This is probably one of the fundamental mysteries of complex analysis. Why is that? Here's the calculation, if you don't believe me. So if I parameterize that circle of radius r centered at z naught, I have this, so I plug in the parameterization, and I do the math. That gives me this, which after Euler's formula, or definition of the complex imaginary exponential, if you like, gives me that. But if we're integrating over like integer multiples of sine and cosine, those integrate to 0. Except one possible case, which is m equals to minus 1, in which case this gives me a non-trivial integral, like we said, like we already saw. So anyway, all right. So direct calculation of complex integrals is tough. Oh, don't worry about this count. The last 12 of them are just frivolous. So if you're keeping track. We also have a complex fundamental theorem of calculus part 2, which is to say if you have a antiderivative of your complex function, you can take the difference of the antiderivative at the endpoints of the curve. The reason for that being true is basically the complex chain rule, which I use somewhere in here, right here. And also these conditions right here are the Cauchy-Riemann equations. So Cauchy-Riemann equations, just writing stuff nicely, and then the definition of the integration, and then this is the going from here to here complex chain rule, and then this is just the ordinary fundamental theorem of calculus part 2 adapted to complex values line integrals. There's also an FTC1. If you have a star-shaped region and you have a holomorphic function on that star-shaped region, you can build a antiderivative by integration. All right. And there's also these like usual topological results. You have the equivalence of path independence, integrals around loops being 0, and finally, if you have two different loops and their boundaries of some sort of annulus where the function is holomorphic between those on the annuli, then you can deform the integral from the inside to the outside and not change the integral. This is the deformation theorem. It makes for some of my most dastardly test questions. I will tell Dr. Majerick all these things. Try to influence your test. But anyway, so Cauchy's theorem. Now we get to something that's a little bit weirder. If f of z is holomorphic and continuously differentiable on D and extends continuously to the boundary of D, then the integral, the complex integral around that boundary is 0. So here boundary of D is the oriented boundary of D, where inner boundaries are oriented clockwise and outer boundaries are oriented counterclockwise as per usual. The proof of Cauchy's integral theorem, excuse me, this is not Cauchy's integral theorem, this is Cauchy's theorem, which is easier. It's just Green's theorem and the Cauchy-Riemann equations. See, if we take this, we have that, but then if you rewrite it, you've just got this, which then, by the Cauchy-Riemann equations, I have these are 0. So, and to get from here to here, what do I do? What's this? I'm going from the integral around a boundary to the integral around the area. What is that? No looking at the slide, that's cheating. This is what?
Calc 3 is 0.
From Calc, yeah. You saying we need to look up their Calc 3 transcript and like change their grade? Is that what you're saying?
Yeah.
Oh, Okay. Do I have such power? I've always wondered. I mean, if you were my student, I think I could just say, I made an error calculating the final. Some of you are worried. But no, this is Green's theorem, right? Green's theorem trades the integral around the boundary of an area for the area integral of the corresponding appropriate partial derivatives of the coefficient of dx and dy. This is actually the complexification of Green's theorem, but anyway, that's easy enough to prove. So Cauchy's theorem has many applications. And so like here's an example. If I was integrating dz over z plus I plus dz over z minus I over, so this is my silly notation for like the circle of radius epsilon centered at I. So gamma epsilon I, this is like this guy here. Down here you've got gamma epsilon minus I, all right? So here's the thing, is I could actually write this first one as the differential of the logarithm of z plus I by choosing an appropriate branch, whatever that means. But that integrates to 0, which is told to us by the Cauchy's theorem, because 1 over z plus I doesn't have any divergence. Like it's totally just, it's a fine function on this circle and within it, right? There's nothing divergent about z plus I, right? I just get 2i at the center of this, like 1 over z plus I does not diverge within this circle here. In contrast, down here, 1 over z plus I does diverge within this circle. So we kind of expect that the integral of this first piece would be non-trivial if we were to integrate around that, whereas it's trivial around that. But that's what Cauchy's theorem says. It says that if you integrate a function which is holomorphic within the curve, you just get 0. All right? And on the flip side, I don't get 0 from this piece because, well, that's kind of the calculation we already did, right? If we have the reciprocal power, we integrate and we get 2 pi I if we go around a circle once. All right. So the next step in this game is Cauchy's integral formula, which is, so, all right, so I've studied calculus over a variety of different algebras, and there actually is a Cauchy's theorem for many other algebras. I've proved Cauchy's theorem holds for like a fairly wide variety of commutative associative algebras with unity, finite dimension. It's not hard, actually. This, on the other hand, is special to complex analysis because there's a very particular structure that complex numbers have that gives rise to this theorem. So this is special. This is special, Cauchy's integral formula. And it says something really weird. It says f of z is 1 over 2 pi I times the integral around the boundary of f of w over w minus z dw. So what this is doing is it's integrating the values of the function around, like, just think of d being like a circle for the sake of specificity. If we think about a circle where the center of it is z, it's calculating the values of the function around the circle and dividing by this thing which is 0 at the center of the circle, right? Somehow that integral over the edge values of the function around the circle is equal to the value of the function at the center of the circle, which is exactly where this expression is not defined in some sense. So like that's really weird. But nevertheless, you prove this, and this actually is proved from Cauchy's. The proof of it involves Cauchy's theorem and sort of a deformation argument. We don't want to get into it here. But once you know this, and if you're willing to do some freewheeling, 19th century style calculus, you just can move your derivatives inside your integrals, right? Because why not? And if you do that, you can derive that this formula implies that formula, which is the Cauchy's generalized integral formula, which is pretty cool. Here's an example of it. So I reproduced the formula for our reference here. This is Cauchy's generalized integral formula. Suppose you wanted to integrate sine of 2z over z minus I to the 6th power dz around the circle centered at the origin of radius 2, counterclockwise oriented. So if you were going to do this directly from the definition I showed you guys, we'd have to parameterize the circle, shove it into these functions, calculate the 6th power. It seems unpleasant, right? So this is pretty cool because we're not actually having to go through the definition of the integral. We just use Cauchy's generalized integral formula, and out pops the answer. This is really, really weird. Look at what's happening. We're calculating an integral by doing a derivative. That's weird. But that is the nature of complex analysis. There's a link between differentiation and integration which we don't find other places. And it is a much reason for the beauty and richness of this topic. But anyway, there you go. We calculated this integral using the generalized integral formula like that. So. I do have some integrals later in this talk, which I think you'll find more calculus 2-ish. Some of these are just kind of just for the sake of illustrating the theorem. But so you guys remember Taylor's theorem, right? So when we look at Taylor's theorem in the light of the Cauchy's generalized integral formula, we see new things. So of course, if we have a power series representation of the function on some disk of radius rho centered at z0, it turns out that, I mean, we know this from Calc 2, right? Calc 2 says the meaning of the coefficient is you take the kth derivative, you divide by k factorial, you plug in the center, that's how you derive the coefficients, right, or interpret them. What's fantastically new here is that from Cauchy's generalized integral formula, we derive that another way to look at that constant is it's actually 1/2 pi I times the integral around the circle of radius r, which encircles that center point, f of w divided by w minus z0 to the k plus 1. In other words, there's an integral which we could do to also calculate the coefficient, right? But what does this mean? Just think about where we're going. So something you might not have accepted in Calculus 2, I know my students have a hard time accepting this truth, which is that if you're given a power series, it allows you to calculate derivatives without differentiating, because you can use the series to extrapolate derivatives. This means that we can do integrals by just looking at the series. That's the lesson here. So here's a proof of it, which I think is worth seeing because it takes us 2 minutes. If we look at f of w over w minus z, we can factor w out, and we get 1 over 1 minus z over w. But that is the sum of a geometric series. So, bam. Which then we can repackage as such. And so if we take Cauchy's integral formula here, and we shove in the geometric series result I just calculated there, and then we do some handy-dandy 19th century freewheeling exchange the integration and the sum kind of moves, which is later justified by a whole theory of uniform convergence and stuff, which I talk about in the course, but not here. Oops. You get this formula. But that is the coefficient of zk, which is to derive that formula we just wrote down. This is the formula for a sub k in terms of the integration. Now I did it for z not being 0 because you don't want to look at it. In my notes you can look it up. It's got the non-zero calculation. The same calculation goes through for a center other than 0, but that's enough suffering. So that brings us to the Laurent series. The Laurent series is something a little bit surprising because the thing we were just talking about was for a function that's analytic, that's holomorphic on a disk, right? The Laurent series says that actually, if you have a function that's holomorphic on an annulus, so between two different radii, and the one radii could be 0, so it collapses to a disk, or the other radii could be infinity, so it could be the whole plane, or it could be a so-called exterior annulus, like outside a donut seems relevant. So if you have a function holomorphic on an annulus, then it has a Laurent series decomposition. This is the theorem. And not just that, the coefficients for the Laurent series are given by an integral around a loop that fits in that annulus, in the interior of the annulus, like that. I can no longer write down the calculus 2 result in all instances because it may not be the case that f of z naught is even defined. Nevertheless, I can calculate the Laurent series by doing these integrals. Or, to flip the script, if I have the Laurent series, I can do integrals, which is actually the interesting thing. All right, so we're getting there. So a function has an isolated singularity at z naught if there exists an R such that it's analytic on a punctured disk. Basically, it has to be, it has to have a well-defined power series. Anyway, it has to be. This is what it takes for the singularity to be isolated. All right. So there's basically 3 things that can happen for an isolated singularity, because we can look at the decomposition Laurent series of it close to the point. The 3 things that could happen is there's like basically no reciprocal terms in the expansion, right? That would be the removable singularity. There could be a finite number of reciprocal terms. This would be a pole of order n. Or there could be an infinite number of reciprocal terms in the Laurent expansion. That would be what's called an essential singularity. These three cases behave radically different. You can identify them from the behavior. The Riemann's theorem for removable singularity says if you've got an isolated singularity and the function's bounded near that singularity, it's removable. Essentially, it's a complex analog of a hole in a graph. You could just cancel it and go on your business, right? For example, like sine of z over z would be an example of this. That has a removable singularity at 0, it turns out. All right? Even though technically sine of z over z is not defined at 0, right? But we can easily define a power series which would get sine of z over z everywhere and define a value at 0 which would be continuous, namely 1. On the other hand, if you have a pole of order n, well, it's necessary that the modulus, the length of the function goes to infinity as you approach z0. And this is for any possible path. It blows up. On the other hand, the Casorati-Weierstrass theorem says that if you have an essential isolated singularity of f of z, then for every complex number w0, there's a sequence zn goes to z0 such that f of zn goes to w0 as n goes to infinity. This is very weird. What it more or less says is that near an essential singularity, you'll find that your complex function takes on all possible values close to the point. It's annoying. And I don't really understand it, but there it is. But so that brings us to, I want to talk more about the pole of order n. That's really where our interest is. That's where the integration theory is, okay guys? So if we have a pole of order n, what that means is that you have just up to order n reciprocal powers, right? And then you got this other piece here, which is kind of like the power series piece of the Laurent series. So this is called the principal part. Now, when n equals to 1, it's called a simple pole. Right? It's important to know. N equals 1 is called a simple pole. N equals to 2 is called a double pole because mathematicians are very unimaginative with their terminology. The big theorem here is kind of like an analog to the factor theorem. If you have a pole of order n, that's true if and only if you can write your function as like g of z divided by z minus z0 to the n. This is useful. Here's an example. If I have f of z is e to the z over z minus 1 to the 5th power, since e to the z is analytic on c, this guy has got a pole of order n equal to 5 at z0 equals to 1. All right. Move on here. So that brings us finally to define what the residue is. So the residue of a Laurent series is simply the -1 coefficient. It's kind of anticlimactic, right? I told you, some of you said this talk was about residues. Well, we finally got to it. This is the definition of a residue. If you want to talk about the residue at z0, you calculate the Laurent series of the function based at z0. Whatever the coefficient is of the reciprocal term, that's the residue. Simply that. For example, if you do the partial fractions, you guys know that from Calc 2. This is the cool thing about Math 331 is that you review Calculus 1, Calculus 2, Calculus 3. It's all in there, right? And you should get better at each of them if you do it right. But anyway, so this is the partial fractions decomposition of this rational function, right? And from this, I can look at it and read off, oh, wait a minute. So this means that the residue at 0 is -1 because the coefficient of 1 over z is -1. And I can also see from this that the residue of like 1 is 1 from this term, right? So, and these other terms, if you think about how they would expand at those points, they just give you power series. This is exceedingly interesting because we have this thing called Cauchy's residue theorem. Cauchy's residue theorem says that if you have a complex plane, rather a function on a complex plane with respect to a bounded domain, and you have the f as analytic in the space except for a finite number of isolated singularities as pictured, well then what you can do is you can calculate the integral simply by doing 2 pi I times the sum of the residues. So if all I have to do is find where the complex function blows up, and I can calculate the integral from those. 4 useful rules. If you have a simple pole, you can calculate the residue like this. If you got a double pole, it helps to multiply it by like z minus z0 squared, differentiate it, take the limit. That's a nice rule. I, in practice, tend to use rules 3 and 4 a lot in examples. But anyway, you guys will see all that when you take the course, so I won't belabor these points here. But we got lots of nice rules for simple poles, right? Simple poles important. All right, so I got 2 examples, and then we're pretty much done. But this is f of z is 1 over z to the fourth plus 1. It has 4 singularities as pictured. Bop, 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 bop. And if we look at this half circle contour, only 2 of those are within the half circle contour. So when I calculate this integral, it turns out it's going to be equal to 2 pi I times the sum of those 2 residues. And you work it out, and you get pi over the square root of 2, which shows us that this improper integral of dx over x to the fourth plus 1 is actually pi over root 2. Now I plugged this into Wolfram alpha. It will give you an antiderivative, but it's involved. It's pretty nasty. Another important example that pretty much everybody covers in Math 331 is how to do a trigonometric integral. So here it's a really sneaky trick. What you can do is, if you look at the integral like around a unit circle, if you make z equals to e to the I theta, it ends up giving you, like cosine theta can be written in terms of z, and sine theta can be written in terms of z, and dz can be written in terms of, well, d theta could also be written in terms of dz. So if you put those substitutions in here, you trade an integral over a trigonometric function you might not know how to do for a complex integral, which can be easily dispatched with the theory of residues. See, because there's only one singularity by the algebra up here, so I can just calculate the residue at that point, plug it in, answer. So then basically complex analysis allows us to do integrals that we probably couldn't have done another way, all right? So that finally brings us to story time. So there's a story I have to tell you guys about. So you have to imagine there's a plane, all right? And it's like a jet airliner, and there happens to be a rabbi, a Polish janitor, and that was supposed to be a physicist. And they're sitting on this plane, right? And it's stormy, and they're just, they're over the ocean. It's bad, right? One of the engine goes out. The pilot has a heart attack, and then the flight attendant comes, and she says, "Is there anybody here who can fly this plane?" And the rabbi's like, "I'm sorry, it's a Sabbath. I can't do it." And the physicist says, "I'm a theoretical physicist. I can't fly the plane. That's not for me. That's it. That's it." And then the flight attendant goes to the janitor, and the janitor says, "But I'm just a simple pole in a complex plane." It landed. It was all worth it. Thank you for your attention. Yes. Oh, I do have some others. That was the best. I also have this. And I have this. Huh? And this. And I did put Einstein in at some point because it's more convincing as a physicist. And you never get like a content strike for putting Einstein. He's not copyrighted. And this one's a little bit I don't know what's it doing. I don't know what it's doing there. And then this one is it starts to make everything Einstein sometimes. As best as I can cipher. I have some more disturbing ones though. I don't know what's going on here exactly, but there's that I don't know what that is here. And this one is actually probably the most disturbing one, just because of, I don't know, like what is that? Like, I hear people singing the praise of AI, but do you really want it doing anything serious? Like, I don't. Good night. Like, imagine being put in the position of having to argue with somebody to undo something like this in a future place where we're using AI in some official capacity. My goodness. And then, that one. And then I kind of like this one. This one, I'm kind of partial to this one. We end here. This is the actual end. So, Anyway, thanks, guys. Oh, if you have questions, feel free.